Hey everybody, it's Mrs. Slauson. We are on page 82 in our pink packet, and we are going to be looking at properties of logs. So properties of logs are going to be very similar to properties of exponents, and the three big properties of exponents that tie over into properties of logs are these three. So I'm going to put these properties of exponents at the top. They should be familiar to you. Okay? So the first one is this rule. And the idea is if you are multiplying with the same base, there's a shortcut that you can do to simplify this down into one base with one exponent. So let's just review what an exponent does. An exponent tells you how many times you're multiplying something repeatedly. So this 2 is telling me that I'm multiplying x 2 times. And then this 4 tells me I'm multiplying x 4 times. And so there's this shortcut, if I look at how many x's are now multiplying, I've got 6 of them. And so the shortcut says if you are multiplying with the same base, that you can just add the exponents, okay? So that is called the power product. All right, product rule, product property, not power product. All right, the next one looks like this. So I'm just going to flip it around, and it's going to present as a division problem. So what is happening right now is my numerator is saying that there are 4 x's in the numerator, 2 x's in the denominator, and then what I can do is cancel out common factors. So remember, factors are the things that multiply to one another. And so this factor can take out this factor because anything divided by itself is 1. And then these could cancel each other out. So when I'm done, I have 2 x's left, and I have them in the numerator. So the shortcut, this is called the quotient rule, the quotient property, says if it's division and it's division of the same base, that you can just subtract these exponents. All right? And this works. Let me just switch this around on you. If it were, I'm just going to put it right here, x2 and x4 like this, then when I break it up, and then I have these common factors cancel out, this time my x2's are in the denominator, and so to have a denominator I would have to make a numerator of 1. So just repeating, if you're multiplying with the same base, the shortcut is you can add the exponents. If you're dividing with the same base, then you can subtract the exponents. The only thing that's going to happen here is you have to decide where do those x's go. And so wherever most of the x's are in the beginning of the problem, after you cancel your factors out, you're still going to have extra x's in the numerator. So because there were more in the numerator, that's where my answer ends up. But in this situation, there are more x's in the denominator. So when I cancel them out, that's going to leave my leftover x's in the denominator. So you can subtract the easiest way possible, all right? And then just think about where your final answer should be, in a numerator and a denominator. And then the final rule is called the power of a power. And so the easiest way is just I'm going to change the numbers to show you the shortcut. Again, an exponent tells you how many times you're multiplying this. So this 3 says I'm multiplying x squared 3 times. So there's once, there's twice, there's the 3rd time. And then if I go back to what I was saying about the exponents here, or even here, that this says there's 2 exponents, or 2 x's. This says there's 2 more x's multiplying, and then this says there's 2 more exponents. So when I look at how many x's I have altogether, I have 6. And so this shortcut says if there's a power to a power, that you can distribute that in and then multiply these exponents. So what's happening is we are either going to add, subtract, or multiply. So keep that in mind because these similar properties are going to happen on this page. But what we're going to start out with is the graphing calculator. So I'm going to shut the slide off so you can see it. And we're just going to start typing these into our graphing calculator. And this just wants me to use the LN button, so it doesn't matter if you have a 83 or an 84 or a non-graphing versus graphing calculator. I can just type this in. So LN20, remember always to close the parentheses, and I'm going to go 3 numbers behind the decimal, so 2.996. And then I'm going to type this one exactly as I see it, so LN4, remember close those parentheses, plus LN5. Oops, but I got too many parentheses here. All right, and notice I get the same answer. And then this time I'm going to do LN2 plus LN10. And notice again I'm closing those parentheses. And finally I get the same answer. So the question is, why does something simple as this result in the same two answers as these two when it's a little bit more complicated? Okay, so just take a look at it. We're going to do one more. So let's try this one. This one just wants me to use the log button. Remember, the log button just has an automatic invisible base of 10. So I'm going to clear out these answers. And the first time I'm just going to type in log 12. Any calculator will do this. And I'll go 3 numbers, so 1.079. And then I'll type this one. Remember to close those parentheses so that your argument here is only of 3. Same answer. And then I'm sure you can probably guess at this point we're going to get 1.079. So how can all of these give us 1.079? And just the last one, I'll do another LN. And just a reminder, LN has a base, that little subnumber of E, that 2.7 number. But yeah, so LN 50. 3 numbers behind, 3.912. Okay. And as you can guess, they're all going to be 3.912. So the big question is, why does this answer and this answer and this answer all produce this amount, and the same thing here and the same thing here? So this rule says if you are adding between your two logs, what you can do is we're going to condense this down. So right now it's 2 terms. Terms are separated by addition, subtraction. We're going to condense this down into 1 term. So if there is addition, what we're going to do is combine it into multiplication. And what will happen is you'll just take the arguments 4 and 5, multiply them, 2 and 10, multiply them to get this simple single argument up here, 20. So, all right. So that is the first rule. And I'll explain again kind of how these tie into it a little bit later. So again, if I just went here, 3 times 4 is 12. Take this argument times this argument, I get 12. And then the same thing's going to happen here. An argument of 5 times an argument of 10 gives me 50, and so does 2 and 25. All right, so basically this is kind of the longer, expanded version. You're going to hear me use that word. I'll use other words. And then this side is more of the condensed side of it all. All right, so I expand it out into a couple of logs, or I can condense it down into 1 log. And these properties are going to become very important when we start solving. So being able to expand it and take it down to 1 term, which means condensing it. So hopefully you're going to kind of guess what's going to happen here. So if I take ln, again, ln is just a base of E, I get 1.792 if I start to round. And this time, what I'm going to do is subtract these. So I'll do ln, make my argument 12, close it, so the argument's just 12, minus ln2. And there we go, we get the same answer, 1.792. And then I'm sure you're going to probably realize that that is also 1.792. So what about this one? Let's try the log. Again, this has a base of 10. This time we're taking a log of a fraction. That's okay. Just a reminder, that argument, which right now is 7/2, which I didn't type it in correctly. I threw in extra parentheses. That argument always has to be a positive number. It can never be 0, and it can never be negative. So just another reminder. So here I'm going to get 0.544. And if I type this in and just separate it out, log 7, subtract log 2, then again I get that same answer. And then whatever this would be, you would get the same answer. So how can I go from here and here and here and have the same answers? Well, if this argument is 6, what I'm going to do is put the argument of 12 and 2 together, 60 and 10 together, to get an argument of 6. And the only way to get from with 12 and 2 to 6, or 60 and 10 to make 6, is you divide them. So if you have, again, this is the more expanded version, and this side will be the condensed version. If you see subtraction between your log terms, what you can do is condense it down, doesn't matter what the base is, and turn that subtraction into division. And this time I'm going to wrap the whole thing in parentheses so that you realize that x divided by y has to be the whole argument. So you put it in parentheses. So 2 quick ways to remember that. I always think that a subtraction sign, oops, you can't see that, looks a lot like a division sign, okay? And an addition sign up here looks like the old way we used to write a multiplication sign with the x. I mean, not quite perfect, but a plus and an x, not too far off. Subtraction and division, not too far off. All right, so let's take a look at our last one. And this time, I'm going to have the natural log of 9. And I get 2.197. And I'm sure you can realize now, again, that my next answer is going to be 2.197. Or if I take the log of 8, let's see what happens here. 0.903. And this one would have the same answer as well. And then finally, let's try a square root as our argument. The natural log of the square root of 5. So 0.805 if I round correctly. And chances are that's going to be the same answer. So let's start out with this one. How can the natural log of 9 give me this answer? And so does this one. So up here when we looked at it, we started with a single number, and then we looked at what would we have to do to these numbers to get to 6, or 60 and 10 to get to 6. So that's what I'm looking here. How on earth could 2 and 3 ever get me to 9, right? Or if my argument is 8, how do 3 and 2 ever get me to 8? And so this rule says, so again, this is kind of more of the expanded version. I'm just going to put an E, and this is the condensed version. So if you're multiplying, and in graphing we would call this like our stretch or compress, sometimes it would be a negative and it would be a flip, then what happens is that y that's multiplying, that stretch, compress, flip, can actually, so let me rewrite this side, move back into the argument as well, just like how we put 2 arguments together. But when it moves back, it's going to be an exponent. So if I move this 2 back as an exponent, it's 3 squared, which is 9. If I move this 3 back into the argument as an exponent, 2 to the 3rd power, so 2 times 2 times 2 times 2 times 2, then that's 8. And then what's happening here is a 1/2, when it moves back, becomes 5 to the 1/2 power, which if you remember in a previous chapter is just the same as the square root. So what's a trick for this one? I don't really have a trick for that, to remember that one's going to become an exponent. But these are the 3 rules that we're going to have to work with. And there's this expanded side, and then there's the condensed side on all of them. All right? So let's flip the page and see what's happening here. Now this one I'm not going to share just because I have shown you how you can just type this into your calculator. This third rule is a little bit more important if you didn't have this math feature where you could scroll up and choose option A. So this one I'm just going to leave out. It's not necessary. We have to cut things out this year. This is one of those things we're going to cut out. But I'll tell you the general rule overall. I'm just not going to do the examples. So if you have a log with some base that's not e or 10, then what you can do is you can rewrite it as a fraction. This is called the change of base formula. And you're going to make a fraction, and you're going to have a log in the numerator and a log in the denominator. And again, you're going to have two arguments, one for each log. And the base will be in the bottom, and you'll have to remember to wrap it in parentheses. And then the argument will be on top. So that's just something, again, it's not very necessary for us anymore just because of our calculator capabilities. So let's talk about these properties of logs that I just spoke with. And I'm now going to explain to you how they were relating to those exponent rules. So there's the logarithm of a product. What happens when your argument is a product? So this side is going to be our condensed side now. And this side is going to be our expanded side right here. So this is what I showed you originally, and then I showed you we could condense it down. So instead of two terms, we just have one term. So that was this very first one, all right? This one right here. So if you have several terms written out and they're all linked together by addition, you can condense them down into one log with one argument, and in the argument you see multiplication. And so this rule is very similar to this rule that we just did on the other page. So if you see multiplication, right, then there is adding. So multiplication of the arguments becomes adding of arguments. So multiplication between the bases becomes you adding the exponents. So I hope you kind of see that similarity between the two. So this is the other one. So if you see subtraction of several terms of logs, what you can do is you can combine them into one argument, and that argument will have division, and that's similar to this rule. If there is division, like division here, then you subtract. So if I see division, I subtract the exponents. And then the last one that this is similar to is if I have an exponent to another exponent, then you can just multiply those exponents. So if you see an exponent in your argument, what it can do is move to the front, and then it starts to multiply. All right? So again, if you see multiplying, multiplying, you add the exponents, you turn it into adding of logs. If you see division in the argument, so division in the exponents, you subtract the exponents, you subtract the logs. And if you see an exponent to a power or a power to a power, so if that turns into multiplication, the multiplication is a little different, it just moves to the front. And then this was that last rule that I told you about, the change of base. And it just remembers that the base is in the bottom and the argument's in the top. So let's take a look at these. Some of these we're going to look at separate, then we'll start to combine some of them. So what happens is these are all single logs, and what we're going to do is we're going to expand them. So when we expand them, because of the property, that will tell us how we're going to expand them. Will there be a sum, or would there be a difference? All right? So let's just start, let's kind of break it down into a few of them here. So we're going to start with this first one. So that's this example. So inside my argument, I'm just going to focus on the argument right now, is I have 4 times e, this 2.7 number. Well, what I'm going to do is turn that times, that's supposed to be my, oh, I didn't do that very well. Hold on a second. Get my whiteout tape. Just a second. All right. Didn't write that correctly. So that time sign, remember a time sign normally in the past looked like an X. I'm going to turn it into an addition sign now. And now I have 2 terms, and whenever we do this, each term gets the log in front of it. So this will be ln with 4 plus ln with e. So let's try another one like that, but we'll step it up just a little bit. Let's take a look at this one. So right now I see 3 times a squared. And when I see multiplication, I'm going to turn that into addition. And then again, when we expand it, now each term, the term 3 and the term a squared, is going to get that log in front of it. So log with 3 plus, and I'm going to leave a space here on purpose, log with a squared. Now, as it turns out, this one has another rule in there. This is the power. So if you see an exponent, what can eventually happen, or what will happen, is this 2 moves into the front, right there, and then my final answer, which I probably should put this up higher, would look like this. Okay? And now the 2 is multiplying to the log a. All right? So with that, let's go to this one. So here I only see x to the third. So as soon as you see an exponent, note that this is the logarithm of power, and that 3 is just going to simply move to the front and then multiply or become the stretch of this natural log if we were to graph it. All right? And normally I wouldn't put that dot there, but otherwise I'm afraid it might look like 31 instead of 3 times the natural log. So this one's very similar to it. Again, just look at this as x squared times y. So the multiplication will turn into addition, and this exponent will turn into multiplication in front. So this turns into the addition. I always start there. And now each term will get the ln in front of it. So ln will go in front of the x squared, and ln will go in front of the y. And then the last thing I do, and some of you will do it all in one step, is I'll just move my exponent to the front. So now it's 2 times the natural log of x squared plus the natural log of y. Let's see, what are some other ones similar to this? So let's switch up the base a little bit. This one. So this is 9 times x to the 4th. Again, that times will move into addition or change into addition. I have 2 terms, and each term will need this log base 3 with it. And normally the 4 should go here, right? But now I'm going to go ahead and just make that step and move it to the front of its log, not the front of all of this. And then the other thing I want you to keep in the back of your head is some of these logs, these terms that we look at, we can replace with the number. So far, all of the logs that we've looked at so far are not something that we could switch into a number. But log base 3 of 9, remember, this is me asking myself, 3 to the what power makes 9? Well, I could switch that into a 2 and do this. What I can't do is make this 6, because remember, adding and subtracting is really picky. This is just the number of 2, and this says I have 4 of these log 3 to the x's, and I can't make 6 of anything, because these are just integers and these are logs, and so you can't combine them and make them 6 again of anything. So let's try some other ones now. Let's try some ones that have fractions in them. And remember, if you see division, take those little dots away in your division sign and it becomes subtraction. So what I'm going to do here is I'm going to start with, and I'm going to write it, sorry I didn't say anything, I'm going to write it left to right, because then that reminds me that this is just going to turn into division. So I'm using a different color because hopefully you won't notice the red dots anymore. So now each term is going to get that ln. Before I do that, I do want to remind you that never in our rules did I show you anything with a radical. So if you see a radical, you should be looking at it as a rational exponent. So a square root is a 1/2 power. So now this term will get ln and this term will get ln. So ln e. And let's go back to this rule. If you see an exponent, it just moves to the front of its particular log and multiplies it. And then there's that minus sign, and then I'll do the natural log of 2. Now this one I don't know. I would be essentially asking myself, let me find a pencil here. Oh, is this a pencil? Sorry, looking for a pencil. I would be asking myself, do I know 2.7 to the what power gives me 2? I don't. But in this one, there's that base of e, and I would be asking myself, e to the what power makes e? So this term right here is worth 1 because e to the first power is right back to itself of e. So this is worth 1, and then I could take 1 times a half and get a more simpler answer of 1/2 minus natural log 2. That's a really great thing if you can do that. If you can't, it's okay because this is all still pretty new. And actually, now that I see it, this one I could have done as well because there's an understood little e here. And I can do e to the what power gets me to e. So I could have changed this term into 1 as well. It's great if you do it. It's okay if you don't. All right, let's try this one now. So here I have x minus 1. All of that is divided by x squared. So what I'm going to do, and I wish there was a little bit more room, is I am going to write it out x minus 1. All of this is divided by x squared. And now that division is going to turn into subtraction signs. And I want you to think of these parentheses as subtracting what's in here, because in the end, x minus 1 will become the argument. And so finally what I'm going to do is take each term, this is a term, it's all together, it's in parentheses, and this is a term, and I'll put this ln in front of both of them. So ln, I'm really squishing this in here, of all of this, this whole thing is my argument, minus, and if you remember, this 2 is just going to jump to the front, so let's go ahead and do that, ln of x. So that bottom row is my final answer. And some of these are tough, you know, we're not jumping into like any of these very simply. So the last one I want to look at is, well, we'll go ahead and look at both of these. So again, right now I just always ignore the log and the base, and I just focus on the argument. So what I see here is a times b squared divided by the square root of c, which I'm going to go ahead and change into c to the 1/2. And now what I'm going to do is take my multiplication. Remember, multiplication can look like addition. And division, take away those 2 dots, which I really can't do, so I just really have to try to make that stand out, into subtraction. And now I have 3 terms, and each term is going to get this log 2 in front of it. So I'll have log 2 with a plus log 2 with b, and the squared is going to jump to the front, and then minus, which I'm running out of room, so I'll have to put it below, log 2c, and then the 1/2 would just move to the front. So if I had more room, I should have written all left, right, and not stacked it. So the last thing we're going to look at is this one. So what I see in here is x squared times the square root of x plus 1. And again, we don't use square roots, we use exponents, so I'm just going to rewrite this as 1/2 power. Since it's all under the square root, it's all to the 1/2 power. And now I'm going to change this multiplication sign into addition. When you see these parentheses, it is protecting everything in there. You're not going to bust it up. So this is just a log. Put that log with this term. Move the 2 to the front. Here comes that plus sign. Here's log. X plus 1 is still there, but move the 1/2 to the front. And none of these are logs that I can simplify like I did in a few other spaces. It's just like this. So those are all different examples of expanding. So we looked at, you know, again, if there's multiplication, switch it to addition, and then each term will get the ln in front of it, or the log with whatever base it is. And if there's division, division will turn into subtraction. And anything with an exponent will move to the front as multiplication. And this is tough. It's not easy. It does take practice. So this one is kind of a nice thing to know, expanding it. What we really have to know is the condensing examples. So this kind of helps you tie it together. Yes, you will be assessed on it, but the next part is more important because this will come into play when we start to solve some slightly tougher problems. So I've just turned the page. I'm on page 84. And let's take a look at some of these now. So here the idea is instead of having 2 natural logs or 2 logs at the base of 10 or even 3 natural logs, what we're going to do is we're going to turn it into 1 natural log or 1 log or with whatever the base is. So in the end, I will be having just 1 natural log. So I'm going to kind of put my final answer right here. And again, what I did in the last one is I really just ignored those logs for a while, and I'm going to work backwards with what I did. So in the other problems, the very last thing I did is I took any exponents and I moved them to the front to multiply. So that's the first thing I'm going to do. Anything that's multiplying to the log, I'm just going to move it right back into its exponent position. And what I'm going to do is still leave this as minus. Okay? And then what I like to do from there is, because I don't like seeing the natural log so many times, is I just ignore it. And then now when I see subtraction, I'm going to change it back into division. And when we write our answer, we write it as a fraction. So here's a little box for my answer. So x squared divided by y cubed. Here we go, x squared divided by y cubed. And then a good idea is just whatever you want to have be the argument, put it in parentheses. Because remember, we graphed what's in parentheses, that h, that's the argument. K, that's something totally on the other thing. It's not part of the argument, so we never put it in parentheses. All right, let's try this one. So the first thing I look for is if there's anything multiplying to my log, even if it's a natural log, I will move it back as an exponent. So I'm going to start there. And then what I like to do is ignore the logs now. Oops, it should be 1. I miswrote things. All right, 1 with a fourth plus x with a half. And now I look at the terms. This is a term, this is a term, and that addition in between the terms is going to turn into multiplication. I'm not going to put an x because I got enough x's. And now what I'm going to do is just write this times this. Usually have the shorter part in first, so I'm just going to write it over here, x to the 1/2 times x minus 1 to the 4th. You could also write it as the square root of x if you want. Not much simplifying I can do here. And then this natural log that I've been ignoring, I'm just going to put it back. So either with the rational exponent or with the radical. And if you want to make sure that everyone understands that all of this is part of the argument, you could wrap this in parentheses. Okay? Kind of a weird answer, and I get that. This will all happen when we start to put this together with solving. So let's take a look at this one. Again, first thing I'm going to do is I'm just going to put those back as exponents. So now that I'm getting a little more comfortable with this, I'm just going to do it right in the problem. So there's 5, this becomes a 3rd power, and this becomes a 2nd power. And then because I don't like all of that, I drop all those logs. And now I'm going to change the addition subtraction in between the terms into multiplication and division. And now I want you to think d division goes d in the denominator, because I don't write my answer with the division sign, I write it with a fraction bar. So I will have log in my final answer. Here's my fraction bar. Anything that's divided is in the denominator. So it's x to the 5th times y cubed. Divided's in the denominator. And if you want to make sure everyone knows that's your argument, put it in parentheses. So that's my final answer. So let's try this one. So there's nothing in front to move back as an exponent. So I'm just going to look at this now as x minus 2 plus x plus 1. And now what's in parentheses? Again, if it's in parentheses, it's protected. This addition sign will turn into multiplication, which you are actually more used to seeing it just like this. And this is just a neighbors meets the neighbor situation, which we're going to go ahead and do. So here goes my final answer. I will have to have the log with it, and I'll have x squared when those neighbors meet. When these neighbors meet, I get 1x, and when these neighbors meet, I get negative 2x, which gives me negative 1x. And then these neighbors meet, and I get negative 2. Now, this one is super important. All of this is part of the argument. So if you don't wrap this in parentheses, then it will be assumed that just x squared is part of the parentheses, and this stuff is just kind of the extra stuff. So like this is the h in parentheses, and these other two things are the k's, not in parentheses. So we have to put it in parentheses so we know that all of that is the argument. All right, let's try just a few more here. So what I'm going to do is take some shortcuts. I'm going to move this 1/2 right back as an exponent, get rid of it, move this 2 back as an exponent, get rid of it, and move this 1/3 back as an exponent, and I'll get rid of it. And then again, what I like to do is just see what I'm really looking at by dropping those natural logs. And now the subtractions become division. And so that means I will need a fraction bar. And I'll go ahead and put the ln in front of it. And if it helps, this one is always in the numerator. Well, usually it's in the numerator. I'm not going to give you any that it wouldn't be in the numerator. But I'm dividing this, so it goes in the denominator. Dividing denominator. And I'm dividing this, so it also goes into the denominator. But since they're right next to each other in the denominator, that would imply multiplication there. I'm fine with the rational exponents. Some people would prefer that you write them as radicals, so the square root of x. Whoops, sorry, that should not be there. And then y squared times the cubed root of 4. And again, just to make sure everyone knows that that's part of my argument, that goes there. Last one. Again, some of these are very challenging problems, but we're almost done. And I know this is a long video. So what I'm going to do is first this multiplication just will go back as the exponent. I'm going to drop those logs so we can see what we're looking at. And just that reminder one more time, if it's in parentheses, do not touch it. It is protected. So this subtraction becomes